Okay, I think we can get started. So welcome everyone. We're going to talk about debugging tools and like how they really work. So just going to start by setting a little bit of context of why I think this is important. And really, I mean, I think debugging is central to programming, right? In fact, programming really is debug. There's programming is made of two parts. There's bugging and debugging, right? There's typing it in and making it work. Like you cannot be a good programmer without being good at debugging. And I would say also you cannot be good at debugging without being able to take advantage of the tools at your disposal, right? And of course, that is not to say, well, obviously we don't need to use all of the tools all of the time, but there are certain times when certain tools come in really, really useful. And all else being equal, one programmer isn't able to make use of the tools available, another one is. All else being equal, the one who is able is going to be the better programmer, right? Programming is also models. It is, what ultimately comes down to, the transistors on the chip. It is impossible for a human to think in sufficient detail, to be able to cope with what's really going on in the computer, right? So so if you're a Java programmer, you've got this model of the JVM and you don't have to worry about, memory management, right? But you kind of do. If you want to be a good Java programmer, you need to know that this thing called garbage collection happens. You need to know that there's this mark and sweep algorithm, and sometimes a thing will pause while that goes off and does its thing. And, in fact, like it doesn't completely take care of it. If you've got references to objects, that are still live, then those objects won't get tidied away by the garbage collector. So you can totally still leak in Java, right? If you're a C programmer, and mostly I think this is, we're sort of talking C and C++ programming in this talk, but that sort of level. But it even doesn't matter. You have this model that you kind of the C model that you're programming to, but sometimes you need to know what's going on underneath. In fact, even if you're writing an assembly code, underneath the x86, if you're writing x86 assembly code, it's micro ops, right? Those instructions are made from micro ops. And if you want to make it, super fast or whatever, you might find that these 3 instructions actually, run a lot slower than this other lot of 10 instructions to do the same thing because of the micro ops it boils down to. So 90 whatever percent of the time, you don't need to think about this. You live in the model, right? But sometimes things go weird and the model breaks down. What they say, or no model is perfect. Some models are useful, right? And you need to know what the boundaries are, and you need to know at least at a conceptual level, kind of what's going on underneath that model that you have. And so you combine the two with the tools, right? The tools give you a kind of model. When I'm stepping through the code in GDB, I have this kind of conceptual model and I'm stepping a line at a time, but what's really going on 90+% of the time, I don't need to worry about that. I just like accept the model that GDB gives me. But sometimes like weird shit will happen. And in fact, then you can find yourself really led astray if you don't understand conceptually what's going on with these tools. And that's, I think, one of the reasons why some programmers kind of eschew all these tools, right? And just use printf the whole time because, one too many times in their life, the tools kind of led them down the garden path and actually took them away from the right answer. So that's why I think this talk is important. Probably preaching to the choir a little bit because you're here listening to me, but hopefully that will convince you to stay. So really, well, debugging, what's another way of saying debugging is thinking what happened, right? I had, again, my mental model of what my program was going to do, and reality has diverged from my expectations, and I need to figure out where that reality diverged. That's what we mean by debugging, obviously. So let's look at the tools available to help us answer these questions. This list, of course, is not exhaustive, but I kind of categorize things into 2 buckets of 2, right? So at the top, we've got the debuggers, what we think of as the traditional, all of these tools are debuggers in the sense that they're used to remove bugs, but there's what we think of as the debugger, right? Typically GDB, maybe LLDB, they're kind of the same for the purposes of this talk. There's also Ptrace, which I've classed alongside with those debuggers. Now, so it's really just what in my program, what's happened, how can I see what my program is doing as it goes? Time travel debuggers, we'll look at those a little bit. For those of you who know me, obviously that's a subject kind of close to my heart. It gives us the control over time. And then the second bucket of two is these checkers. So the debuggers really are just generic program comprehension tools. I've got this bunch of code, it's doing something, let me understand what it's really doing, right? It's not actually looking for the presence of any particular bug or other, right? In fact, sometimes they're useful just to get your head around how some complex piece of code works. You might not even be actually debugging to get used to these things. The other two are the checkers, right? And these are looking for instances of certain classes of bug. I mean, a buffer overrun is the classic, right? But of course, there are all kinds, race conditions, deadlocks, memory leaks, all kinds of things, right? And it's kind of like there's only, there's only 7 different stories or whatever they say, and there's probably only, most bugs kind of fall into one of these categories. So these checkers can just look for instances of those anti-patterns, and tell you when you've done them. And there's 2 kinds. It's dynamic, so it's a running program, and static just looks over the source code and finds the where they might be. And again, pros and cons, right? So the dynamic ones, you've got to actually trigger the bug. If the buffer overflow is kind of hypothetical, then most of these dynamic checkers aren't going to find it. They're only going to spot the buffer overflow when it actually happens. So maybe you've got a vulnerability, but if you're not under test while you're running in these checkers, you're not going to see it. Whereas the static checkers will analyze the source code and kind of tell you what might happen. So I'm delighted in this talk to be joined by Dewang from Coverity, from Synopsys, the Coverity people, who's going to talk about the static checkers, because he knows way more about that than I do. But that's kind of how I would categorize these different things. So to recap, the debugger is, what is my program doing? One way you might think about that is, there was this cinematography technique that was made popular, really made popular, I think, with the Matrix, and then got used all the time in that kind of early 2000s period, where they would try to freeze frame, and then the camera would pan around while time is frozen, right? So the bullet's in midair, and then the camera would come around and you'd see it from all kinds of angles. And that's kind of what the debugger does, right? It stops the program when you can see everything, and you can maybe move it on one frame, or you can just continue the action and pause again and have a look around. So that's what my program doing. The time travel debuggers tell you what your program did, right? Gives you control over time. So if I go back to that metaphor, it's like I'm in the editing studio and I can wind the tape back and forth to when the bullet was fired, but I can then stop and look all around at any angle from that point, right? So complete visibility of any point in the program's history. So incredibly powerful. And then we've got we come into checkers. What are we saying with the dynamic checker? We're really saying, did this thing happen? Did a buffer overflow happen at any point? And if it did, I want you to tell me exactly where it did, right? Because the trouble with, one of the things that makes bugs hard is how long elapses between the bug itself and you noticing the assertion failure, or the seg fault, or the bad result being produced. And the longer that gap is, the harder the bug is to fix, right? And so the sanitizers and Valgrind and these dynamic checkers will just go, right, there it is. That's where your buffer overflow happened. Straight down to that line of code, very useful. Static checker, could this thing happen, right? Could the program possibly do this thing? Now, one of the problems with that is you've got this real problem with many programs could do all kinds of things in theory, right? But in practice, will they really? And that's kind of what really separates the different kind of static checkers and kind of gives you the value on those checkers. Okay, so that's kind of the context. We're going to look at some of all of this stuff today, and let's start though with the debugger, with good old GDB. Let's start to look down. How does that actually work? Well, so here's my super fancy diagram. I'm not very good at drawing these things, so you just have to put up with it. Anyway, so GDB controls the process being debugged. Sometimes in the GDB documentation they call it the inferior. Controls the inferior through this thing called Ptrace, right? Which is a kernel API specifically for debugging. It allows one process to go and monkey around with another and inspect its state, and actually even change its state as well. And then GDB will find out when the program has done something interesting by receiving a signal. So let's just go through this just before I go into that. So let's have a look. Let's look at what we're talking about here. So I think I've got a Hello World program here somewhere. Yeah, there we go. So I'm going to do -G3, always use -G3. We'll talk about why in a bit, but I think that's a very useful thing to be doing unless you're super short on space or something. I'm going to compile my program. I'm going to run it in GDB. You probably know all of this, right? So here I am debugging my program. If I Control Z from that and PS, I can see my process tree, right? So here's my GDB process, and here's the process that I'm debugging. Now, if we go cat proc that PID, I liked it when in the old days when PIDs were shorter and you could reasonably type them in. Status, we'll see this line, right? Look at that. That's the tracer PID. That's the PID that is ptracing a.out. And sure enough, 1617130, that's my GDB, right? So GDB has connected to my process over ptrace. And also note, this process is in this state T, tracing stop, right? So what does that mean? Well, let's come back to this little diagram. So, sorry, I've got slightly out of step there. Let's talk about. We'll come back to that tracing stop in a moment. So, just back up a little bit and talk about signals, right? So I said the tracer gets notification of interesting things that the tracee has done via signals. So think about Linux and Unix signals here. So when a process receives a signal, the kernel will do kind of the following. A little bit of a simplification. It's a model, but it'll do. So it might, well, most you kind of think about this, terminate the process. Most signals by default will terminate the process. Not all, but most will. Some of them, so sigint, for example, just terminate the process. Some of them sig-v will cause it to dump core, maybe, like if it's so configured. The signal might be ignored. The program might have decided to ignore signals. It might go into a stop. So if you send sig stop on some others, like sig t stop, which is a terminal stop, and sig t tin and sig t out, that will also suspend the process that receives it. At least by default, that they can all, except for sig stop, they can all be overridden. Maybe this program's installed a signal handler, and the signal handler might run. Or if it's being p-traced, it could go into this tracing stop that we just saw, right? So if the process receives a signal and it's being p-traced, it will go into a tracing stop, and the process that is tracing it will be notified of that signal. Signals, with the exception of sig-kill, which is a bit special, will never actually directly kind of hit. Well, they'll never hit the debugee. They are the tracee. They are sort of intercepted by the kernel. Doesn't send them to the tracee. It puts the tracee in a tracing stop and notifies the tracer. So in our little GDB thing we just looked at, right? So we got a hello world program being debugged by GDB. In this little diagram, doing red boxes mean that it's stopped. It's in a tracing stop. So I'm at the GDB prompt. And then when I type continue at the GDB prompt, it's going to issue a ptrace cont call, and that will wake up the hello world process, and up it will go. It will run. And it'll just keep running until at some point it's going to receive a signal or terminate. And in neither of those cases, what happens is the signal notification will go back to the tracer, and via a wait PID call, GDB will be notified that something interesting has happened. Usually I've received a signal, or possibly the process has terminated. And it's all signals, right? So the only way so when you type continue at GDB and it runs it runs the inferior, resumes the inferior. The only way you're going to get back to that GDB prompt is when the inferior receives a signal, or if it terminates. So when it hits a breakpoint, actually, that's a sig trap. When it and the process will get a sig trap, except the process doesn't get the sig trap. The tracer sees the sig trap. When you do Control C, at least if you run like I did just in that little example, if I run the process from within GDB, it doesn't do anything special. Actually, it's just they happen to be GDB does make the process, when you type run, GDB will make the process the controlling the foreground process of the terminal, so that when you do Control C, all of the processes in that process group, which do just the debugging, well, they'll all get SIGINT, right? Except they don't actually get SIGINT because it's being ptraced, so it goes to GDB, and then GDB will, by default at least, not send that that signal in. So here's essentially what happens, right? So this is what the kernel does. So if the signal is sig kill, then that doesn't matter, right? It doesn't matter if you're being ptraced. It doesn't matter if you tried to install a signal handler. I mean, you can't. It doesn't matter if you tried to mask it. You can't. Sig kill, process dead. That's it, right? Almost as kind of uncontrollable as sig stop, and that will suspend the process. Again, you can't mask. You know, the process cannot mask it. You cannot install a signal handler for it. These two signals are special, and they will always do the same thing. Otherwise, if the signal is blocked, masked, then it just gets marked. The kernel just marks it penny and continues. This is true even even in the case that you're debugging it, right? Even if you have a tracer. The block signal is just GDB will not be aware. If the program receives a signal that it's masked, GDB doesn't get to know about it until such time as that signal is unmasked. There are some exceptions to do with hardware signals. If you've masked, actually, that maybe is a little interesting thing that we could talk about. If you've masked, say segv, for example, and then you segv, maybe you've got a seg, or maybe you've got a segv handler, and the handler runs with segv mask, and then the handler segvs. Then the kernel will, in that case, the kernel will replace the handler with the default handler and unmask the signal, and then GDB will be aware of it in that instance. But generally, if you mask a signal, the debugger doesn't get to see it. And then if it's being traced, right, if that tracer PID is non-zero, then the process goes into a tracing stop, and there's a wait PID notification that goes to the tracer, so GDB can know that something interesting has happened. Or if the signal's ignored, then we can just ignore it. If there's a handler, run the handler. But if you're being ptraced, like, you don't get to these second two else's, right? And finally, if none of them, then terminate the process, and you don't get to these last three else's. If you're being traced, it just the process goes into a tracing stop, and the debugger gets to see that's happened. So let's look at like some of. Whoops, I didn't actually mean to do that. Let's do that again. So if we look at some of, let's look at some like what that means. So come back here. So I've got some example. I've got an example code here with the masks SIGINT, right? This basically, this program, very simple, does sig proc mask to mask SIGINT, and then it just sort of goes into a loop forever, just sleeping, right? So if I run that, so -G3, always -G3, and then I run this in GDB, run. So normally I would expect to be able to Control C and interrupt it, right? But that doesn't happen. I've got no way to get control of that. That's a bit of a bummer. Or if I did Control Z there, and it got a different signal. It got the sig terminal stop, and now I got back to the prompt. Another way I could do it is actually to. I've probably got two GDBs. So I don't think I've killed. No, I've only got one. Okay, good. So PID of a.out. So I can kill. So here it is. Look, it's still running, right? I can kill sig stop to that. Actually, I can probably do this. Can't I? This one. So kill sig stop a.out, and voila! Look, it's received. It's received the sig stop, right? Okay. So if your program is masking signals, and sometimes programs do, right? They're quite common to mask all signals and do something. You're trying to run that inside the debugger. You're going to find, damn it, my Control C doesn't work. But the good news is they can't mask sig stop, right? Programs cannot mask sig stop, so I can always fire sig stop at it and get control back. In fact, internally, GDB will use that as well. So if I've got a multi-threaded program one of the programs receives a signal, hits a breakpoint or whatever, one of the threads hits a breakpoint or whatever, then GDB will actually go and fire sig stop to all of the other threads in that process, all under the hood. You don't see this, can hoover them all up and then return to the prompt, safe in the knowledge that there's no way those signals can be masked or have a signal handler or anything. Okay. So we went through this. Sorry, we have to go through this again. So I'm not going to go through the Ptrace interface because it's quite broad and it's quite horrible as well, actually. It's a really crummy interface. It has a single call and then it has this opcode as the first argument. I always think that's an anti-pattern. If you have an opcode as the first argument, which probably means you should have a whole bunch of different functions, and then you get like some kind of type safety and the rest of it. Anyway, Ptrace doesn't. I think it's inherited. It's definitely inherited from at least Solaris. Maybe, probably. I think it's even the original Unix. And so sort of a bit of a legacy API. Obviously, not many people need to use it, only if you're fortunate enough to be writing a debugger. But it's good to know kind of what it's doing. There are loads of them, right? So I'm certainly not going to go through all of them. And this isn't even a complete list. It's quite an extensive interface. But I am going to go through these three just very briefly. Ptrace cont, Ptrace single step, and Ptrace syscall. So Ptrace cont just going to resume you issue it when the tracee is in a tracing stop, and you issue a Ptrace cont to it, and off it will go, right? And it'll just run until the next time it encounters a signal. If it's already got signals pending, it won't make any progress. It will just stop immediately. Or I can do Ptrace single step. Not all architectures support this. This does require that you have architectural support in the hardware. Most modern CPUs do. x86 certainly does. Modern ARM CPUs do. Older ones maybe don't. But anyway, what it does is it'll run exactly one instruction, one CPU instruction, and then it'll stop with a sig trap. And so that's you can imagine how that gets used sometimes for implementing next or step type commands. Although actually often what GDB will do when you do a next is put a breakpoint and the next line and continue. At least it will when it will actually do a repeated single step, I think, unless it leaves the function, in which case it will continue until it returns. And then there's Ptrace syscall, which doesn't have any architectural support. It's entirely a software thing. And that will run until the next time that the tracee issues a syscall. And then the kernel will fabricate a sig trap and it will stop there. So that's quite useful, right? Particularly for tools like strace. So you actually get 2 sig traps per syscall. If you use Ptrace syscall, you get one on syscall entry and another one on syscall exit. This is actually configurable, but that's usually what you get. If you happen to be writing one of these, you can actually distinguish between syscall entry and syscall exit, as in the way in and the way out, by looking at AX. Bit of a hack, but if it contains -38, which is sys, then it means it's a sig entry. At least most of the time, doesn't quite happen all the time. You are just expected to keep track of that yourself. So here's a really kind of, I haven't even tried to compile this, but this is basically how strace works, right? So a really, really simple strace. Not going to have, of course, it can attach to running programs and all the rest of it, or strace, or however you like to pronounce it. So it's going to fork the tracee, the program that's being traced. And then the tracee issues this trace me Ptrace call, which sort of causes its parent to trace it. And strangely enough, it's quite surprising actually sometimes in some ways. But yeah, the tracer doesn't kind of get any choice. It's just like the child can decide that the parent's going to trace it, and then do exec. Exec will actually, whatever's happening, exec will cause if it's being traced, will cause a sig trap to be received. And then in the parent, we just go forever, wait PID on the PID that's stopped, and then in that status, just sort of crummy wait PID interface, but you get to see what's happened. So if it's not with stopped, which could be it's signaled or exited, basically that means the process is terminated, so we're done. Otherwise, I haven't shown the implementation of this, but you can imagine how it might work, right? I'm going to go and show the syscall and print get the registers to see what the arguments of the syscall were, etc. And then off I go again, Ptrace. So the first syscall will be exec, and then we go again with the Ptrace syscall. And this will actually end up with 2 lines being emitted per syscall, one on the way in and one on the way out, but that's fine. Notice this thing at the bottom, right? So you pass in the signal from the Ptrace call, and that's the only way that a traced process will actually receive a signal is if the tracer feeds it back in from its Ptrace const, Ptrace syscall, or Ptrace single step, right? So the tracer in strace or GDB has complete control over what signals the tracee will actually get, with the exception of sigkill. So that's kind of how I'm gonna. That's hopefully that's kind of all reasonably clear. I'm going to let's just. I've got a feeling or let's just do one more thing on signals, because this is kind of screwy, but kind of an example of what I'm talking about, where you can get led astray if you don't really have a good understanding of what's going on underneath. So we looked at my mask int little program just now. I've got another one very similar, mask trap, right? That's pretty much what you think. So I'm explicitly raising a sig trap. Now, this is kind of interesting, because if you raise a sig trap while you've masked sig trap, actually, you're still going to receive it. And then GDB tries, I think what's going on, I haven't actually checked the source code. I think what goes on is GCC tries to be a bit clever here. So GDB, sorry, tries to be a bit clever here. So so if I'm going to start the program, I'm going to go into TUI mode. So if I sort of do it in the normal way, if I just continue my program, it just runs through to the end, right? It's masked sig trap, it raised sig trap, it didn't see it, and GDB kind of works out what was supposed to happen, what it thinks was supposed to happen. If I start again, and if I start doing, if I next, and if I now get this right, if I put a breakpoint, I think if I put a breakpoint on line 18 and continue, poor old GDB gets very confused, because it kind of sees the sig trap. It kind of knows that there's a breakpoint roughly in the area, but you might, if you're eagle-eyed, you'll notice the GDB will normally say, I've hit a breakpoint. I've hit breakpoint number 2. Because sorry, I've hit breakpoint number 3, because that's what is set there. But it kind of got very confused. So it got the sig trap. It wasn't quite sure whether there's a breakpoint or not. And I think if I continue from there, then I get a segv. So poor old GDB's got really confused now. I think it's not quite managed to step off the breakpoint or something correctly. So this is something that it's perhaps worth just going into a tiny bit. I think we're doing okay for time. Yeah, I'll just go into this tiny bit while we're here. So, as you may or may not know, when you set a breakpoint, GDB writes a breakpoint instruction into the text, right, into the executable memory. A breakpoint instruction on x86 is OXCC. That's the opcode, single byte opcode, because that's kind of important, right? Because x86 is a variable length instruction set. Some instructions are only 1 byte. If the breakpoint instruction were more than 1 byte long, and I had to set breakpoint on 2 adjacent instructions 1 byte apart, that would be problematic, right? So the x86 designers kind of thought of this right back in the original x86 days, and made sure that there was a special a trap instruction, OXCC, written int 3, but it's special. If you write int 4, int 5, it will generate interrupts on those of those interrupts. And that's 2 bytes, the int opcode and the operand. But int 3 is special for debuggers. So GDB will write OXCC into like whatever address where the breakpoint resides. You can't see it, right? If I let's restart this program. And so if I if I put a breakpoint, let's put a breakpoint on line 13 and run to it. Now, if I if I look at the disassembly, I don't see the int3 instruction there. That's the original code, right? Because what GDB will do is write in all of the breakpoints only before it continues the program. And then when the program stops, it'll put it all back to what it was. So it's kind of transparent. It's difficult to kind of see what's going on. But what happened just now when I got that segv, I haven't looked into this detail, but I'm pretty confident that what's going on is, right, so when you've hit a breakpoint, when you continue from that breakpoint, you don't want to just hit the breakpoint again, right? It's kind of a special case, right? So if I continue from a breakpoint, what GDB will do is do a Ptrace single step without setting the breakpoints, and it'll step over that instruction, then put all the breakpoints back, then continue, right? When it hits the breakpoint in x86, at least, it does depend on the architecture, it will stop with the program counter at the instruction one after the OXCC instruction. So GDB also, when it hits the breakpoint, has to unwind the instruction. And what I think we saw when we got that segv was that GDB was getting that wrong. It got confused about whether it hit a breakpoint or not. It either subtracted one from the program counter when it shouldn't have, or didn't when it should have. And then you're in all sorts of trouble, right? Because x86 is a very variable length instruction set, and you can start executing from the middle of instructions, and it gets very confusing. So what's the moral of this story? Using GDB on programs that use sigtrap for something is a bit dodgy, basically. Best avoided if you can, and best avoid putting any breakpoints where you may also hit the sigtrap. And if you do, just be aware that everything might not be quite as you wanted it to be. Okay, let's talk a little bit about syscall restart. So here's a really simple program, right? It's got an empty, a null signal handler, and it's going to attach that signal handler to the sig alarm. This alarm function, if you don't know alarm, it just means that in 5 seconds after doing alarm, the process is going to receive a sig alarm. Then it does this read that's going to block, and unless you type anything at it, and then 5 seconds later, the sig alarm is going to come in, the handler is going to run, and read will return eintra, right? That's how signals in Unix land work. So I've got that almost that program. It's slightly, I'll show you that here. It is eintra. So I've actually done sig action rather than signal, so I want a little bit more control. So always -G3 eintra. So if I run that, and I've actually changed it to alarm 2 because waiting 5 seconds is a surprisingly long time in a demo. So run the program, 1, 2, finished. Good. But if I type something at it, then it aborts because read didn't return the eintra, it returned what it read, right? Nothing sort of too surprising. If I run it in GDB, I'm gonna now. One thing I need to do here is, I should have said this before, actually. Let me show you now. So, remember we said that, show info. Remember we said that with the exception of sigkill, the only way signals actually hit the program being debugged, the tracee, is if the debugger so decides that it sends them in. And this setting in GDB controls what it will do for each of the signals. Most of them, you see this yes, 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 right? So you do what you kind of would expect. So it stops the program. It prints a little message to say that you received, let's say, this is an unfortunately common one. We all know and love it, I'm sure. So it'll print a message, program receives segv after it stops the program. And then if you continue, it'll pass that segv back in, right? And if there's a segv handler, that will run. If there isn't, then it's the end of, that your program is dead. But no, they're not all yes, yes, yes. So sigint, for the reasons we discussed earlier on, right? It'll stop the program. It'll tell you it's received a sigint. When you continue, it won't pass that sigint into the program, at least by default. So if you're debugging a program that has a sigint handler and depends on that sigint handler running, you're going to get confused and surprised and disappointed when that doesn't happen, right? So I can change that. I can go handle sigint stop print pass. It will warn me. It'll say, this is a kind of a bit of a special one. Are you sure you want to change that? And I think actually probably I don't want to change that. And just like, because I don't know why, I guess the GDB designers at some point decided that sig alarm was kind of common enough that you probably didn't want to know about it. I think maybe actually early versions of the libc sleep call, and maybe even modern versions do it, I don't know, but certainly early versions of libc sleep would use alarm, were implemented in terms of alarm. And you know, perhaps it'd be confusing if you were debugging and you've got all these sig alarms kind of popping up all over the place. So it kind of hides them from you unless you ask to see them. Again, you know, if you don't understand what's going on, then you know, this can confuse you. So I do care about the sig alarms in my little program. So I'm going to handle sig alarm stop print pass. And I think I already started my program, didn't I? Yeah, here I am. So just going to 2 mode. I'm just going to continue the program. And after 2 seconds, oh, there we go, got my sig alarm. Now, and I can continue, and it's going to run the handler, and then it's going to return, and everything's fine, right? So at this point, my model of what's going on kind of all makes sense. Like if I just run that again, you'll remember how I've set to handle the signals. So it stopped when I'm kind of inside the read syscall, right? The kernel is in the read when it receives the sig alarm, and it kind of looks like I'm in the read, and it's right after the syscall instruction look, right? If I continue, it will actually continue that read, although the read will return eintra because that's what it does, right? So actually, just go once again, and so here we are. We've got the sig alarm, and I'm going to go out of TUI mode. Might get this wrong. So I'm right after the system call. If I step instruction to see what happens next, bonk, I'm up into that signal handler, right? Signal handler doesn't do very much, but I can run that. And if I step off the end of that and get this little, and here I am at the end of my read, and I can see it's returned, actually it's returned something that is surprising. Why? That's not what we expected, right? Why is it returned 3276? Well, it hasn't actually completed that line yet. I guess that's just whatever was there. Run it again. And okay, yeah, it's returned -1, and there is 4, which I happen to know is eintra. All good, right? So the model is kind of holding up at this point, but we're going to go. We're going to eat the blue pill or the red pill in the matrix. I can't remember. Whichever pill lets you know what's really going on. I think it's the red pill. Anyway, so when the read happens. Okay, that we get a call down. This little lower block is the kernel, the upper block is my program. So it calls down into the kernel. The kernel itself will have a whole bunch of function calls that happen, right? And it'll end up down in the depths of the file system, although this is a read from the terminal, so in the terminal handler. And then it blocks, right? Now, when my signal comes in, what happens is this then starts to unwind. So my sig alarm happens, right? And the kernel will start to unwind back up, but it doesn't return back to where it would have. It returns not straight after the read, but into the signal handler, right? And when the signal handler returns, actually it returns via the kernel. There's a little system call. We'll see this in just a minute. It does a sig return, so it can unwind any kind of kernel state and everything, and it goes back to there and it returns the intra, right? So we can start to see, but when it's being traced, actually, you know, there's this SA restart. If I program my signal handler with SA restart, it will cause the read to resume when the signal handler returns. And what the kernel actually will do there is, this is transparent, the user space will never see this, but it'll actually return from that read. After the signal handler's run, it will return
e restart sys, not e intra. E intra is 4, e restart sys is 512. It's not a regular erno. Actually, the kernel returns negative of these, negative e restart sys rather than negative e intra. And then the kernel's kind of clever, and when it's resuming, it will, from a system call with e restart sys, will actually restart the system call. In fact, what it does on x86 is subtract 2 from the program counter to reissue the syscall instruction. And we can see this. So I'm going to run it again. And there's a, see, it takes a long time, doesn't it? Good job I changed it from 5 to 2. So here we are. If you remember, we've received the signal, but right after that syscall instruction, if I look at RAX, which is the register that contains the return result, it doesn't contain -4, it contains minus 512. And because, in fact, if I change my, I'm going to change my program so that what was it? Which was intra, wasn't it? Intra. Let's make it a bit longer so I get a bit more kind of start. Got to remember to do that. And if I run, whoops, so if I continue, it'll, and I can Control C, same deal. I can continue. It goes back into that syscall, right? It goes back into the read syscall. And when I continue, again, it's because it's got that magic 512. And so the continual calls that syscall to restart. Now you should never, the user space should never see that negative 512. Actually, there's a few of them. As you restart this, you restart block, you restart no hand. And so some of them, things like clock, nano sleep, some of the other sleep functions will adjust the timeout so that when you restart them, you know, otherwise you might have a sleep with a timeout of 5 seconds, or a poll or something with a timeout of 5 seconds, and an alarm that's going off every second. And if it restarted, properly restarted that poll with a 5-second sleep every time after seeing the SIG alarm, then the poll would never time out, right? Because it would always go back to 5-second timeout. So it actually, the kernel's quite clever. It will restart the poll or then sleep with an adjusted timeout, and so you can, that's another, it knows whether to do that with another sort of code. So why does this matter? Well, if I'm looking at return results and syscalls, I might get kind of confused, right? I might have no idea what -512 is. That looks wrong. Also, there are bugs in GDB and in some versions of Ptrace where these leak. So user space should never see that. When you continue, the kernel is supposed to transparently just restart the syscall, so the user space never gets a chance to see that return code. Doesn't always happen that way, and in increasingly rare circumstances, that can leak. Particularly, though, likely to happen on Red Hat Enterprise 6. That kernel, they backported this thing called utrace. So remember I said that Ptrace is kind of a sucky interface, and it is. And some decent people said, right, enough of this. Let's design it properly. They made this kind of modular thing called utrace in the kernel with a Ptrace kind of compatibility layer onto it. This was being used a lot by the dtrace stuff, system tap, and so Red Hat wanted that in, so they backported it all into Rails 6. And it never really worked properly. It's always been a bit unreliable. And in the end, it got dropped, and they did things differently. And so it's all just regular Ptrace. So debug, so using, using Strace or GDB or anything that uses Ptrace on Rails 6, it's a little long in the tooth now, but there's still a lot of it out there. You can see there's quite a few bugs, actually. Very, things are signal heavy and very threaded. You can see this restart sys will leak sometimes. There are other problems with deadlocks and things not terminating when they should. So, if you can't always avoid it, of course, you might be investigating an issue that only happens on Rails 6, or that's the machine you happen to be on. But if you can avoid it, with GDB, I would say avoid. Kind of covered all this stuff actually. Yeah, okay, there's also debug registers on x86, which are used for watch points as well. So you can actually do it without writing into the code, and that can be useful, but there's a limited number of those, right? There's only 4 hardware watch point registers. Okay, let's get on to let's get on to this dwarf info, right? Which is, so when we've talked about ptrace and how that can, the process goes into to tracing stop and ptrace around, and we can do ptrace get regs and ptrace peak to see the memory in the registers, but of course GDB and the same, by the way, it's going to apply to Valgrind and address sanitizer and things. They don't tend to talk about program counters because that's not very useful, right? They give us lines of code, and we can look at, you know, we can look at, we don't have to look at memory addresses. We can say print the value of foo. And this is all done by the dwarf info, which essentially will take a program counter. It'll say for every program counter what it maps to a source file line and even column actually. And it'll give information about what the types are and the variable names and everything. And so the debugger can parse this dwarf information to see kind of what's going on. And we're going to have a little bit of a look at that, some of that as well. So and we're going to talk about something that we've probably all seen only too many times. So if I go GCC -G3, always 3, and so this is what -G3, it actually produces more, better, later version of dwarf, and puts more stuff in there, and it's much better, like inline. Even it can even do macros. So we've got preprocessor macros. The debugger can now understand them if you do -G3. And inlines work a lot better, and generally it's all better. But I'm going to give it some optimization, and going to run it like that. Okay. So now, here we are. Now print foo. Probably all seen that message, right? How annoying is that message? GDB can't tell me what the value of foo is because it's an optimizing compiler. In fact, if we look at the source code, what's this? The source code, the assembly. What's this doing? Well, it's okay. Got some sort of preamble stuff here. Calls random. Okay, fine. Put some stuff into registers. Like at no point does it load the foo. Its memory. Foo is entirely held in a register, which you would kind of hope, right, with some optimization. So poor old GDB, how's it going to know? Well, actually, because I partly just does this anyway, but particularly because I did it with -G3, it does know when it says foo is optimized out. What it really ought to say, I think it'd be much better if it said it's not live yet. I'm at the beginning of line 7, right? So foo doesn't exist. It's not been optimized away. It just doesn't like exist at this point. If I step forward. Wait, that's not what I expected. I don't know what happened there. And oops, next, no. Weird. Okay. That's not what I expected to happen. Let's put breakpoint on line 8. And now print foo. Now it's got it, right? Now, even though it doesn't exist in memory, right? It's not, if we looked at this, remember the disassembly. I'm sure I tried this earlier today. It worked. Really good. Anyway, okay, all right. So, and I can have a look. I can look at that with readelf debug dump of a.out, and we can start to see what it tells me. So here it's, and there's a variable called foo, right? And it's in file number 1, which is the only file in this source code, and that's the line where it's declared and the column. And it's got this locations list, and it says it's location A, OXA. And if I do debug dump equals lock, we can start to see some of the detail of what it tells me. So
In fact, so I can go side by side with GDB and we can take a look at the disassembly. So it's telling me that this is that, remember this location A for foo, and it gives me some offsets in the file. So these will be offset by page numbers, but it ends at basically 108 and 1098 in the file, in the text file, which is here. So it says from here it's kind of live, and it's kind of clever. It says it's in RX, and then actually if I look at my disassembly, it's in RAX and EDX as well, and it tells me from this offset 109C it also exists in RDX, but also look, it doesn't exist in EAX anymore from here onwards, right? Because the value of foo is just in EDX, but now it's saying from this offset 1086 it is now I can see it back in RAX, right? And there I can see it's this LEA is actually just adding 1 to EAX because that's what the program does. So so nicely, even though I don't know why it's behaving differently today. It's the demo effect, isn't it? But look at that. I didn't do anything different. That's mad. All right, okay. For some reason now it's working. And so now foo is live and I can see the value. And notice my print increments foo, and it's a post increment. I can see it's still got it there. So it's kind of almost not quite got it right because it said it was 384, so it kind of done the increment before at that point. But we can actually see a bit clearer if we step through it. But I'm a bit concerned about time because I want to give Dewang a chance to talk. So I think we'll move on from there. But anyway, the point is that there are times when the variable is live. And modern versions of GCC with -G3 in particular will do a better job than you might think with that stuff. Right, so that's all that. I want to get in. Oh gosh, we are running out of time. Right, just very quickly on stacks and frame pointers and things. Right, so optimized code is often going to omit frame pointers, but we can still find out where the stack frames and things are. Very quickly, what I mean by frame pointers, just in case we're not familiar. So here's an x86 stack which grows down. My program does some stuff. The stack pointer moves down because it's like done some stuff on the stack. It does a bit more stuff. The stack moves down, does a bit more stuff. And then I'm about to call a function. So the return address is pushed onto the stack, and the function is called. And that function does more stuff, and then it's going to call a function. So its return address is pushed onto the stack, and it does some stuff, right? Now, if I'm compiling with a very low optimization, my compiler might use frame pointers, and right below every return address on the stack, it calls a pointer to the previous frame, and it also burns a register. Frame pointer register that points to the stop. So at all points, that frame pointer points to the top of the frame, and it's a linked list, right? It can follow that, and that is a pointer to the previous frame. So by some pretty simple walking of the linked list and arithmetic, we can unwind the stack. And so when I'm in GDB, I can type backtrace, or some of the things like some of the tools like we're not even going to talk about today, ltrace and things like that. We'll use this to be able to walk the stack. But it burns a register, right? And registers are very valuable things. So optimizing compilers don't like to do that. It also wastes a bit of stack space, which probably doesn't matter, but might. And it takes a bit of time because it has to mess about with the frame pointer on each function entry next. So optimizing compilers think this is a bad idea. And actually, you don't need it because if I know where my stack pointer, I can know for every program counter what the offset is from the stack pointer at that point in time to the stack frame. So if we do this example again, it can say, well, when it's here, I know that the stack frame is whatever, 12 bytes below where the current stack pointer points. And then as it goes, we can just keep knowing that, right? We can know for any line of code how far the top of the stack is, the top of that stack frame is from the stack pointer. And this is what they call beautiful animation. So CFA, call what is it? Call frame addresses, right? And again, this is in the dwarf information. It allows us to walk the stack without having frame pointers, and actually is used by exception handling. The exception handling stack unwinding code will use this CFA and CFI information. So it actually gets used by runtime as well. Oh gosh, I need to go through all this again. Put those slides in order. Right. Skip over that. Very quickly, threads. So the debugger knows about threads. ThreadDB is a library that you can link against the debugger, which is able then to figure out sort of companion library with the thread library. So most threaded programs on Linux these days are using NPTL, but not all, right? And you can have your own thread library, and obviously programs like programming languages like Go do different things, and so you can have your own libthread, which is kind of companion library to the threading library, and that allows the debugger to kind of know stuff like thread local storage, which is important actually for Erno. Erno is thread local. A little plug here for our GDB Watchpoint series. So you can go to the Undo website and go to GDB Watchpoint and look at all kinds of nifty tips and tricks. Dog is not included. Gosh, we really are really going over time. Right, address sanitizers. Let's go quickly through this. So, and Valgrind. So these are the dynamic checkers, right? And they work by essentially, but they kind of work in the same way. They essentially give you a map of which addresses are valid and which are not. You could you might think, well, that's what the page table is for, right? So why don't we just use that? And you can, in theory, but that will really explode the space that you need. If you're going to have every single local object, an int on the stack or something in its own page, that's going to be very, very expensive in terms of memory, and also probably very bad for performance as well, because it will ruin the cache and everything. So instead, they kind of have this shadow memory, which is a kind of software version of page tables, if you like, and it's this data structure that will, for any address, will tell you whether or not that memory is valid. Address Sanitizer uses quite a clever technique to sort of really compress that down, so its shadow maps can be quite small. I mean, it does depend a bit, but generally an eighth of the memory that your program is using, yet still do byte line stuff. And they kind of put these red zones above and below, right? So why do we need red zones and the shadow? And the answer is, well, that otherwise, how do I detect? I can't really detect buffer overrun in that case, right? If I don't have red zones, because the memory immediately after this malloc will also be valid, just like it's different, right? So I put red zones before and after. They're not a page; they're typically sort of 32 bytes or something, and then we can detect buffer overruns. Most buffer overruns. If I overrun the buffer by a large enough amount, I might step right over the red zone, right? So the sanitizers and Valgrind won't catch everything. So this is kind of so address sanitizer is obviously, it's a compile time thing, and so if your code might have done this, just dereferencing address, or reading or writing the address, then the compiler generates code that is poisoned, error, otherwise just do it, and that is poisoned is looking through those shadow maps, and it's got a quite clever optimized thing, so the overhead's quite low. And it can also do it with locals as well. So address sanitizer is better than Valgrind in this respect, because it will put sort of red zones around locals, and can detect that, whereas Valgrind won't know to do that because it's not a compile time thing. Valgrind works with compiled code, so it's a big advantage, right? Because maybe I don't have the source code and I can't recompile, and so Valgrind is very useful there. Or maybe I want, maybe the bug goes away right? You can imagine, alignment things and stuff just sort of disappearing when you start doing this. So Valgrind is very useful in that sense, but it does have the limitation that it's slow and that it can't catch quite as much stuff. All right, so having spent all that time, let's talk about time travel debugging, completely different thing. I'm not going to give a demo. I can assume you know roughly what it is. There was some stuff on it at Lunch and Learn, but essentially just in some words, right? So we let you see any piece of program state. So in the debugger, we can step back a line, not just forwards. We can put a breakpoint and run back. Or the really cool thing, we can put a watch point and run back and do a reverse continue and not run back until that data changed. So this means we can go back to any line of code that executed and see the complete program state, which is pretty awesome. But awesome in kind of more the traditional sense of the word, actually, if you think about it in terms of like, that's a lot of data to store, right? And clearly we can't, obviously it would be absurd to think about storing the full program state for every single instruction that executes. So you think, well, how would we do this? Well, maybe we can just do it a bit like a sort of MPEG encoding. We'll just store the differences, right? So an instruction executes, it's only going to touch a few bytes, probably. So I can just kind of encode that, and that shouldn't be too bad, right? But even that is very slow and consumes huge amounts of memory. Because every instruction is going to change some state. Otherwise, you've got, unless it's an infinite loop, right? It must change at least some register state or some memory state, or at least the program counter. Otherwise, it's halted. And so every single instruction. Well, how many instructions do you get? Well, let's just do some really crude arithmetic. Gigahertz machine, billion instructions per second. That's like gigabytes per second, right, of state that's changing, and that's just too much. So instead, there are time travel debuggers, earlier versions of time travel debugging that just did that, right, and they lived with it, and it's fine, and it kind of works for small programs. In fact, GDB has an inbuilt process record thing that does exactly that, and if you've ever used it, it's extremely slow. The reason it's extremely slow is it's doing a Ptrace single step for every single instruction, and so that is very, very heavyweight. But also generates huge amounts of log because it's like gigabytes per second, or like what would have been a second. So more modern time travel debugging or software failure replay things, the RR and live recorder or UDB, the undo debugger, what they do is to recompute prior state, right? And that's much, much more efficient. And it's sort of based on a fundamental kind of, well, on the observation that computers are fundamentally deterministic things. If I run a program multiple times, every time I give it the same starting state and every time it gets the same set of inputs, it will always do the same thing, right? This is why random numbers are difficult to generate. Well, except, the catch is that computers are completely deterministic, except when they're not. And of course, they're not completely deterministic, because if they were, it'd be kind of useless or very limited use. I just run them once, got my answer, that's it. And of course, there are multiple points of non-determinism. So anytime we make a system call, or a thread switch, or we get a signal, certainly an asynchronous signal, certain non-deterministic instructions or access to shared memory. These will do different things. Same program state, same instruction might give different results. What these technologies do is to store in an event log all of the non-deterministic thing. And then if I want to go back a line, we'll go back to the beginning or back to a snapshot, play forwards to like just before that line, right? And then it looks like I've gone back a line, as long as we've recorded record time, all of the system calls, all the shared memory accesses, etc., so that I can now replay them to make sure that the replay does exactly what it did in record time, right? But you also need a very precise notion of time for this to work, because let's say I'm stepping back through a loop. So the small, it's a mem copy type loop. I want to step back one iteration of that one line within that loop. I don't want to go back to that line 5 iterations previously, or the first time around the loop. And of course, programs are all loops, right? If you don't have any loops, then your program is going to terminate very, very quickly. So for this to work, I need to know when to stop. And I'm replaying, I need to know exactly when to stop. I also need to know when to replay some of these asynchronous events. If it's an asynchronous signal, I need to replay that at exactly the right time. Otherwise, my program is going to do something different. There are two ways to kind of do this. Well, at least RR and LiveRecall to do this in different ways. So RR will use CPU performance counters to count the number of retired branches. That is the number of branches that are actually executed. And this is quite good because the hardware will do it quickly. Makes it quite a simple implementation. But on the downside, they're not always available. And the big killer is they're not available in most AWS and other cloud machines. You get an AWS bare metal or complete socket, they'll allow them. Otherwise, they don't. Basically, multi-tenant cloud machines tend to turn them off. And they so it just won't work in those environments. And there are things you can't do, particularly around shared memory. So the other way you can do it with JIT instrumentation, and that's what LiveRecorder does. Now that does impose runtime overhead. It doesn't, not as big as you might think, but there is some because we're doing more stuff in software there. But it doesn't mean we're not relying on these sort of quite exotic CPU features. So just work wherever. And it does mean that it gives you more flexibility to do things like deal with things like shared memory and weird kind of non-deterministic instructions. Otherwise, it's difficult to trap. So that is so I've rushed forward. Apologies for rushing through that. Oops. Yeah, poor timing, but hopefully that was interesting and made sense. I'm now going to switch over to Dewang, who's going to talk all about static analysis.
Thank you very much, Greg. Hey, everyone. Let me. All right, static analysis. So when Greg take you through all these different advanced techniques for debugging, right? From a static analysis perspective, I generally like to put it this way. Usually, if you have found these anti-patterns, then the question is there a way to formalize and benefit your team by coding up some kind of analysis that catches this kind of problems in the future? Yeah. So this portion of my talk is focused around giving you a little bit more feel for what static analysis is, and walk you through a demo on what it's like creating a static analysis check. So static analyzer, you can think of it as a compiler. You start out with the source code, right? And it will essentially compile your code and generate the semantic representations of your code. So the abstract syntax tree, and then it will compute the different flows that your program could take. And that's a control flow graph. And it will collect other properties. And then what it will do is we'll go through these different paths and look for problems, right? So in today's demo, I'll show you, for example, if you were to allocate memory, right? And then if you your function exits and you forget to deallocate, right? Then you're leaking memory, yeah? So a good analyzer will give you annotations and tell you the paths it took to get to a problem and tell you exactly what the problem is, right? And then you can consume this kind of information inside your IDE in command prompt or through a browser, right? So here I am going to show you an example of a problem that a static analyzer is good for in terms of finding. Yeah, so on the left, we'll see here's example code, test code where we make a call to malloc, yeah? And here is a simple conditional expression where sometimes it will free the allocated memory and other times it won't, right? So when this function exits, obviously you can potentially leak this memory, yeah? So on the right-hand side here, what I have is an example checker, and I'm a solutions architect at Synopsys. I work on the Coverity product, and this is our domain-specific language called CodeXM. And so Coverity can, out of the box, find you tons and tons of issues but you can create your own analysis with it as well. And this DSL is available with the product. And so if we start out at the way bottom here, you'll see that I have defined a checker named after me, right? And so this is how it looks like. I'll say, okay, report for going through all functions in the code base where the function path match the sequence, right? And then I'd say wherever there is a allocation and anywhere downstream in the path where it's missing a call to free, right? And so if we look further up, okay, so I'm gonna define a call to a function called malloc. See the function identifier up here? Yeah, and I'm gonna define it as a node step, okay? And then similarly, I'm gonna define a pattern called call free, and where the identifier is a function free, right? And you'll notice there's some syntax here that just says, I want to make sure that the call to this free function takes an argument, yeah, because we want it to be this form, okay? And then this next two pattern is built on top of the above, right? And one thing that's really important I want to highlight here is in this particular pattern, what we want to say is it's a pattern of this call alloc up here that matches this malloc, right? But one important concept here is I want to point out is if you think about the call graph, you want to line up the malloc with the free to the same address, right? You don't want the malloc of some other memory to be paired up with free of some another memory. Then it's mismatched, right? So you always want to make sure they're lined up. So this key is used to express that. So basically, you can see now we just built a checker that would say every time this malloc, before it goes out of scope, we need to free it, yeah? So let me switch over to demo. Okay, so here is a demo code, and you will see, in fact, the one I talked about just one slide ago is this example code here, right? But I also want to share with you a couple of quick static analysis concepts, yeah? One of them is called aliasing. So you can see that I have allocated 2 blocks of memory here, yeah? And then you'll notice that I declare another variable name, and then I assign it to this one of these addresses, yeah? So that's aliasing. So if I free this address, right? So in our case, Coverity actually can keep tracks of aliasing and these kind of assignments for you for free, right? So because we free this particular address, but we have not freed this one, right? That checker I showed you earlier should then be able to catch the case when this is being leaked. Okay, and of course, the concept with the control flow is you notice in the checker example code, I did not explicitly have to code up for looking for these different paths, right? So again, with Coverity, it's kind of computed for us for free. It just automatically knows that there's a branching condition. So there's a path where this can be skipped, and then there's another path where it's not skipped. Yeah. So let me run this. So this is our checker that I showed you guys earlier. Okay, so the way Coverity works is we do conf build, we specify an intermediate directory, and then we call the compile. So I'm in the Microsoft Visual Studio environment. So I'm gonna do this code. Okay, so now that okay, there we are. So, right, so you can see that Coverity has successfully picked up this compile. Yeah, so now we're gonna run analysis on it. I'm gonna disable all the default checkers, and I am just gonna run the particular checker that we wanna run. Okay, so you notice it's found those 3 instances of resource leaks. Yeah. So now you'll see, okay, so for the simple case, right, there's an allocation, function goes out of scope, it's leaking this memory, yeah? And then here is the second one, right? It's found in this particular case, we have allocated this block of memory, but this one was not freed. Yeah, so this is aliasing. Okay. And then finally, here we allocate. There's a case where we do not go into this block of code to free it, right? Then it leaks. Yeah. Okay, so hopefully that gives you a feel for static analysis. I know that's really quick. The thing I want to tell you guys is if you guys think about if you do code reviews, there's going to be a lot of things about your application that only you or your team will know about, right? The sequence of allocating and you forget to deallocate, this kind of anti-pattern, it's actually really common, right? If you think about this, like if you have a program, let's say, if a function returns a value and you forget to check this value in a certain way, well, it's a sequence of function calls, right? So did you call this function finally or not, right? So it all belongs to this similar type of anti-pattern. Yeah, so, all right, so Greg, I think that's gonna be my portion on static analysis. And maybe we can turn it over to Q&A.
Yeah, so there were some questions which kind of tried to answer in the chat, but as we have a few minutes, we can kind of go into maybe a little bit more detail on them. Yeah, so Honey asked which command was used to see the code while single step, right? So I think let's just look at, so I'm going to, just give me a second here. So that was GDB TUI mode. TUI stands for Text User Interface. So if I share, and we can see that. So yeah, so this was like when I was going GDB So start, and then I can do layout source, and that's pretty cool, right? I often say this is the scores the highest on the least known, most useful GDB command. You can also do it with Control XA. I can also go layout ASM, and then I get the assembly code. And I can step through that. SI is short for step I, and I can step through that. I can actually go, I don't know how to do this to come up. I can go Control X2, and I get both source code and assembly. And I can go Control X2 again, and I get my assembly and my registers, which is kind of neat. So let's see what other questions we were asked. So writing, so GDB writes these in 3 instructions, right, when it's going to put a breakpoint. And question from Mike was, when it's single steps, puts all the in threes back, and then I'm sorry, puts all the normal instructions back, and then the real code back, unpatches the int threes and steps over the breakpoint. How does that work with multi-threading? I tried to answer this in the chat, but I realize now I think I answered a different question. So it will step just the thread that has, so Ptrace gives you control over each thread. So it will unpatch all the int threes. In fact, it unpatches all the int threes before it goes back to the prompt. And then when you continue, it'll single step that one thread over that one breakpoint instruction, then put all the int threes back, then resume all of the threads. And then there's another question, follow-up question from Mike is, how does that work if the replace instructions is a potentially long-running syscall instruction? So again, I sort of tried to answer it, but I think I probably answered a different question. So what happens if you put a breakpoint on the syscall instruction, and I don't actually know. Shall we try it? Why don't we try it? I think this will be interesting. Cat intra. I've got short enough time now that if all goes horribly wrong, I just can duck out without being too embarrassed. So feeling very brave. Something worse when it goes wrong in the middle of the talk. Right. So this has got a nice long-running instruction. So start. So let's go Control A, Control 2. So I get my assembly code. So where's the syscall? So syscall is, oh no, it's inside the beginning of the library. So I'll continue until we stop in the syscall. Right, and so now, oh look, that was dangerous. Yeah, okay, 2E mode with assembly is maybe not the best thing to be doing because GDB's just crashed. That needs debugging. Right, let's do a diff thread instead. So I'm just going to run, and then I'm going to, right, so now here's my syscall instruction. So, by the way, GDB by default will turn off address space randomization. So this is quite useful. So I can just remember that because now I've gone past the instruction, but I can restart and put a break point on that. Let's just make sure that that is, I'm not talking nonsense, and that really is a syscall. Yep, there's a syscall. So let's put a breakpoint there. So I can do that like this. Start, and then the address, and a breakpoint there. So I'm going to run to that. It's going to hit that breakpoint, and then I'm going to continue over it. What's going to happen? Hit the breakpoint, continue over it. Yeah, of course we don't know, do we, whether it, I guess it doesn't matter because it just goes back into the syscall. So that will return when it returns. But would the other threads have started when I did that? Good question. Don't know. We need a multi-threaded program. I need longer than it's going to take longer than this, longer than the remaining 3 minutes to find the answer to that. But I might have to go and look at that. I wonder whether GDB gets that right. I wouldn't be surprised if it just doesn't get it right and none of the other threads run. but it might know its syscall instructions. It could, if it's smart, it'll know its syscall instruction and not single step it, but do a Ptrace syscall. There's another question. No, presumably, so Mike says presumably Ptrace will send a signal back to GDB for the syscall instruction when it's executed. I think, well, it probably will if it does. If GDB starts with Ptrace syscall, I think that's what will happen. But yeah, I don't. If it starts with Ptrace cont, I don't think it will. I'm going to go out on a limb. I'm going to bet. I bet the GDB gets this wrong, but we'll find out. We'll find out. And then there's another question from Charles. How will CPU instruction reordering affect search debugging? And actually, it kind of doesn't. So, having said at the beginning, it's all models, and you need to know what the models are underneath. Actually, I think CPU instruction ordering on x86 is one where as far as I know anyway, I don't know of any instance where you would need to know that. It is completely transparent. The silicon, the chip is sort of clever enough when it gets a signal to kind of, uninterrupted, it sort of unwinds everything and makes it all as if, the instructions had execute all of the instructions up until a certain one, all the instructions before the one when you stopped have executed, none of the ones afterwards have. So it's basically completely transparent. You'll only see it, I think, in terms of performance. You do get exposed to things like memory ordering, for multiple threads accessing memory, some of the sort of weak guarantees that are given in order to do efficient multi-core and multi-CPU package systems, and some of that you can be exposed to. But I might be wrong, but I think that is one, as far as I know, instruction reordering is something that we can all just forget about unless we are really trying to squeeze every last sort of nanosecond of performance out.
Greg, we have a question from Richard Northcott.
Yeah.
His question is, regarding static analysis aliasing, what are the limits of this? Thinking of nested function calls, etc. That's a great question. So there's no hard answer. There's no hard number. Basically, I think you're kind of bound by CPU and memory. But basically, if you think about the control flow graph, static analyzers will take a depth and a breadth first type of approach to make sure as many paths as covered as possible. And in a product like Coverity, we can limit how many paths we want, and we can expand that to be massive. And so, and then along the different paths, the different aliasing that it encounters, it will keep track of them. And so when an analysis like this occurs, it will apply for whatever it's able to pick up, right? So the whole idea behind static analysis is, in runtime, you only can hit the different paths in different cases based on the tests you have, right? And static analysis in some ways is kind of confined, but this time is limited on how much compute and how much memory you're willing to give it.
Cool. So that's there we are at time. So yeah, thanks for doing that with me, Dewang. That was great, and thank you everybody for listening and some really good questions. So yeah, at least some of you were awake the whole way through. So that was pretty cool. It's interesting. It's the first time I've done this remotely. The one thing I thought I really missed is, the demo we did with the optimized code, and somehow it did something different. I must have done something wrong, and that's the sort of thing where if we were doing this live, some kind soul from the audience will have pointed out what I'd done wrong, but because I can't hear anybody, it's still a mystery. So if anybody spotted what I got wrong there, I'd love to know. I must have done something wrong. But yeah, so that's it. That brings us to the end. Thank you very much, everybody. Hope you have a good remainder of the conference.
Right. Thanks, guys. Thanks, Greg.